I'm going to talk to you today about a joint project with Lindsay Currier, a graduate student at Harvard, and Ed Glaeser, who's here, about infrastructure inequality. We're going to look at costs of road roughness and how they're distributed across the US. And our main goal in this project is going to be measure at a very granular level on local roads, as well as other roads, road roughness. We do this as by way of motivation because we see that there's a lot of disagreement about just what the state of road quality is across the US. The American Society of Civil Engineers, on one hand, points out or rates the US roads as deteriorating over time. Gilles Duranton and co-authors in a recent paper actually document for highways that there's been an improvement over time. The key problem is that, especially for local roads, we lack systematically available data on road quality. We're going to move in this direction in this project using data from smartphones of Uber drivers that we use to measure vertical bumpiness of the ride of the trips that drivers are making. We're going to use this data as an input into creating a measure of a road segment, road roughness measure. And the key advantage we want to highlight for this type of data more generally is that it has the promise of very high spatial coverage as well as high temporal coverage. So previewing a bit beyond what can be in our paper, we see the potential for systematic data collection of this type by fleets of vehicles, whether they belong to city governments or companies or other bodies, as well as autonomous vehicles. This data, in turn, can be used, having information on road quality at a more granular level to assess the efficiency of investments and how cities maintain and repair their roads, and more generally used in the policymaking process. And number three, what I'll show you today, we'll show in the direction of measuring inequality in infrastructure at a very local level. So today I will describe the data we have and the methodology that we use to construct road roughness. I'll show you a validation exercise, and I'll tell you about the validation exercises that we do, that we've worked on a lot to convince ourselves that this has signal. I'll then briefly sketch a model that we use in order to summarize road roughness into a cost number. So to understand what are the costs of roughness through speed, and finally give some stylized facts about inequality in the US in terms of road quality and how cities repair their roads. Let me begin with the data. Every smartphone nowadays essentially measures acceleration at a very high frequency, so around 5 times per second, in the 3 directions relative to the smartphone. We are using data that Uber collects from the drivers' smartphones throughout all of the trips. Uber has an algorithm that realigns these axes and is able to give us the vertical acceleration dimension relative to the road rather than to the smartphone. This is going to be our primary input, this bumpiness in the vertical dimension of a portion of the trip for an Uber driver. We then take all of this data and map match it to road segments that you should roughly think as covering one block or one segment between 2 intersections in the road network. This is a map that's based on derived from the OpenStreetMap at a particular point in time. We mainly use one cross-section for the entire US, all of Uber's trips in August 2021, as well as a panel of multiple months in Chicago in 2021 and some data in 2018. Now, first, let me show you that there's signal in a very visual way. So here, as you can see below, we're looking at one trip from the O'Hare Airport to downtown Chicago. And you can see vertical acceleration in the top graph, and already some patterns start to emerge. So on the highway part, we see a smoother and less variable vertical acceleration and a lot of variation at key points during the trip. Let me show you this another way. The graphs that you are seeing now are showing one segment in Chicago, one road segment that is traversed by a railway at grade in the middle of the segment where I'm pointing now. In the second graph, you see all of the data points we have of vertical acceleration of all of the trips that are passing by this road segment. And you already see the wealth of data that we have for just one segment. And moreover, you see that where this railway is, we really have a huge jump in the variance of vertical acceleration. And you see this another way in the bottom graph. Okay, and this is just one segment. Next, I'm going to switch to the methodology that we use to take all of this data and get a measure at the segment level of its roughness. We begin by taking the individual acceleration observations and computing the standard deviation for each segment R, for each trip I, taking all of the observation that that trip has on that segment and taking the standard deviation of vertical acceleration. Now, this is a raw measure, and the key challenge that we will have with using it to directly interpret it as road roughness is that drivers have an endogenous response to rough roads. They're going to drive slower. Okay, so this will tend, if we use this as our measure, this will tend to make us underestimate differences in road roughness. Fortunately, we have abundant data so that we're going to estimate the entire relationship between speed and this bumpiness measure. Basically, leveraging the fact that we observe drivers going over, or Uber drivers going over the same segment with different speed levels. And this allows us to get this entire slope. Technically, we'll estimate a regression where this raw measure is our outcome, and we're interested in both an intercept and the slope that are segment specific in how speed affects this raw measure of bumpiness. We also include some fixed effects for drivers, dates, and hour of the day. We do multiple robustness tests to make sure that we are adequately controlling for how drivers choose speed. And in the end, our measure of roughness is going to take this relationship and then plug in a fixed speed. So we're going to choose 20 miles per hour for local roads. This is the median speed that we observe in our data. And the thought experiment is, if we saw drivers going exactly at 20 miles per hour over this segment, what amount of bumpiness would they experience? And we do the same for arterials and highways and use different speed levels. What I'm showing you here on the right is Cook County. And for each road segment, we're plotting for local roads this predicted roughness. You can already see a great deal of variation. You can see a discontinuity right around the border of Chicago with rougher, lower quality roads inside Chicago that I'm going to come back to. Briefly, we do a lot of validation exercises. I'm going to show you one and briefly mention others. We use the International Roughness Index, a widely used and accepted measure of road roughness collected by the DOT, state DOTs and published in the HPMS, which is available for highways and arterials mostly. And in Chicago, in Cook County, we compare this with our measure. Okay, and these are the correlations that we observe. They are highly correlated. This correlation is not perfect, and behind this discrepancy, there might be temporal differences in when the measurements are made, as well as the fact that we're using different maps, so not exactly the same road segments. But by and large, this is encouraging to us that we're capturing a common signal. We look at national level DOT IRI versus Uber roughness in New York City, comparing pavement condition index with Uber roughness, looking at how roughness varies at railroads and so on. And across these exercises, we're encouraged by how we see Uber roughness moving. Finally, I want to show you in Chicago as a last validation, we collected data on very precise road segments that were repaired in 2021. What I'm showing you here are two graphs with experienced bumpiness for roads that were repaired in May of 2021. You can see bumpiness going up initially, probably during construction area, and then going down after repairs are over. And conversely, speeds going down during repairs and going up eventually relative to the baseline period on these segments. Briefly, so I'm short on time, so let me discuss what we do with. We have a model where we want to quantify two benefits of smoother roads. One is that there's less discomfort when driving, and an indirect benefit is that commuters drive faster, and the time that they save is valuable. Okay, so from a private perspective, we want to combine these benefits into one cost measure, and this model is going to allow us to do it. Let me skip these details to saying that we can estimate the model using a variation in roughness between at the border of towns in the US, and find that total private costs that we find are almost half as high as the speed costs alone that we observe as people drive faster on smoother roads. This gives us that one standard deviation in roughness, or a road that's one standard deviation rougher than the median will cost drivers 23 cents per mile more than the median one. And the model is designed to make it easy to use alternate assumptions here. Now, at the end, let me show you two exercises of how we use this data, and we begin using this data to get some insights about infrastructure inequality. We can aggregate our measure from the road segment to census tracts, and we're showing here Chicago and New York City. We can do this at census blocks and census tracts level. And I'm going to show you today two levels of inequality. The first, that higher income towns generally have smoother roads. And second, that higher minority towns and census tracts tend to have much worse roads. Okay, so these results are shown here for the New York, Jersey City metro area also persist at the national level as well as within MSAs. So going from a 0% Black census tract to a fully 100% census Black census tract increases these costs of road roughness by 9 cents per mile. Finally, we can look at how cities decide which roads to repair and how well they target their maintenance work. And we find here that cities differ significantly in this targeting. New York City here, we're showing which roads are repaired in red compared to our measure of roughness. And we see that there definitely is an upward trend, but lower than what our measure would predict might be potentially optimal. Whereas a city like Dallas, this relationship is much more muted. Let me end here, leaving this slide, and thank you again for including this paper.